Able to hear me now? Okay, yeah. So I will try to stand close to my laptop. I'm not sure how well my microphone is, but if it's like very quiet, let me know. I try to be louder. This is a little bit. I'll do the start recording. It's already recorded. Yeah. All right. Let's see how well this will go. So I was saying this is one of the simulation environments that we have built, trying to understand the possibility of running large-scale autonomous system. In this case, the tiny white dots are drones. We can also build vehicles on the road. You can also put people on the road and all types of robots that we want to serve our community. So if I imagine this is like if I give actually the simulation environment was built in the game engine, it's pretty much like a game. I give you a game where you're supposed to control thousands of drones to make sure they all reach their destination on time without colliding to each other, without being smashed to the wall if there's a strong wind. How would you play that game? If I think about this problem or this game and the challenging problems that we could face, there are definitely a lot of challenges. But here are a couple of things that we are particularly interested in, and it will be the focus of the talk today. First of all, of course, a lot of agents. How would I even control thousands of agents at the same time? How would I coordinate all of them? So if they all squeeze in a corner, how would I make sure that they don't really collide to each other? The second problem would be high-dimensional space. Then being relatively vague here, this space does not only mean the state space, it could be the input space, could be the uncertainty space. So with a high-dimensional space, a lot of the approaches will have exponential growing up with respect to the dimension of the space. How would we deal with this type of problem? A third one would be unknown or imprecise model. This especially goes to two types of things. One is back to the old MATLAB age when people want to build their systems in Simulink, this type of environment. And then the model really becomes so complicated, like there are blocks being connected to each other. You open one, you see more, and you don't even know where the end is. How would we grab a model out of it? The other aspect is environmental uncertainties are really something we have very less knowledge about. How would we deal with the unknown or imprecise models? And lastly, complex requirements. So to really make use of these autonomous systems, autonomous robots, we don't just want to tell them you have to go from point A to point B. You want them to collaboratively serve us. And if they're able to process some complicated specification or requirement that we have in mind to be a little bit more specific, like things like temporal logic-based specification, how would we deal with those in large-scale autonomous system? So I will touch a little bit about some of the challenging problems. I have to say that this, of course, not an exclusive list of all the challenges, and I'm not claiming that we have solved all these challenges, but we definitely have made some very promising progresses that I want to share with you and hear your thoughts on how would we do to follow up on this and tackle even the next level of challenges. So when I think about large-scale control problem, of course, it's not a problem that's being just started by us. It's being studied for a long time, for decades, and there are a lot of very promising approaches that are available there to help us solve the problem. And I know, like, you must have worked on one or multiple of them. When I look at these approaches, again, this is not an exclusive list. There must be something I'm missing here. But my point here is that whenever we deal with like a large-scale problem, we always have to make trade-offs. So here, the trade-off is assurance level versus scalability. Of course, like for example, the traditional control-based approach, optimal control optimization-based approaches for solving control problem we usually get a pretty good assurance level because you know, like this is the right way of formulating the problem as a mathematical problem by solving the problem. If the solver is able to tell us here the solution, we can believe that the solution will give us the optimal solution. So we have we can trust this result. Now the consequence is this type of approaches is normally not that well scalable to high dimensional or large number of agents. So there's still a challenge there. I will mention a few when we really touch the problem. On the other side, on the other extreme, I know a lot of you work on reinforcement-based approach. They are definitely very promising approaches that could tackle highly complex problems. Well, how to make sure they always give us the results that we want? How would we understand the assurance behind the result that RL give us is the open problem. I know people are studying this problem. As of now, it's still a very challenging one. So we see these kind of trade-off. Now, of course, there are other approaches like MPC is kind of doing better instead of assurance in terms of scalability, but still certain things that is hard for us to understand how to prove, like liveness properties for MPC problems, still something people are studying. Now, what we are doing is something called the neural certificate-based control. I know some group at Penn is also working on similar problem. So you might see this being familiar, but hopefully by the end of this presentation that I can convince you that neural certificates approach kind of have the promise of breaking the tie and achieve good assurance level at the same time being scalable. Of course, there's no free lunch. I will tell you that what we are going to lose here by using like neural certificates approach. But in my deep heart, I feel this is a very promising direction to kind of get out of this trade-off. Now, when I say certificate, I first want to tell you what I mean by certificate. There are different types of certificates. Certificate, here is some sort of a mathematical proof that we want to construct. And there are different problems for control problems, for planning problems. I will start with certificate functions in control. And a lot of you are already super familiar with different types of certificate functions in control. I will be very brief here. Now, at the high level, we have studied three types of certificates. The Autonomy function for certifying stability around an equilibrium point. Barrier function that certifies an invariant set. If safety, you can form it as an invariant, then it can be used for safety. And contraction metric. Contraction metric is like a differentiable version of the Autonomy to some extent. And now, instead of certifying the convergence to a static equilibrium point, you can track an arbitrarily changing dynamic trajectory. That is particularly useful when we're working on vehicles and you give a reference you want the vehicle to follow, and that reference could be arbitrarily dynamic but feasible, then contraction metric would be useful for us to track that reference, even if there are external disturbances. Of course, there are other types of certificates. And you can also find a subset of this. You don't have to certify one thing at a time. There are ways of constructing multiple at the same time to certify multiple properties. You can actually certify all of them at the same time. But I will start with the middle one here, barrier function. I trust a lot of you have already known barrier function, so I'll be relatively fast here, but let me know if you feel like I should talk more about barrier function. A barrier function is also quite close to a Lyapunov function, but instead of converging to an equilibrium, we want the system to stay within a safety region or invariant. Now, how it works for a barrier function, it is a scalar function that maps the input, the states, and here for as an initial definition, allows input the x, which is a state vector. It will output a single value, a scalar value. We want this scalar value to be smaller or equal to 0 when states are safe and greater than 0 when it's unsafe. Now that's kind of tell you why it's called a barrier function, because h equals 0 is going to be a barrier that tell kind of like a classifier that tell you what is safe, what is unsafe. That's it. Then that kind of boundary is our barrier. Now, the third condition here is what makes it a control barrier function. So we want the time derivative of this function h to kind of always be negative. So that in that sense, you would never get across the safety barrier. Like in the safety region, you are negative, if your derivative is negative, you will never get across the barrier. So that's the high level idea. But you also don't want it to be so, strict. You can always stay away from the unsafe region. You can, so that alpha function there is a class K function. So what it's doing is say, you can get closer to the barrier, but when you're really close to the barrier, you probably want to turn around and stay away from the barrier. So that's what the last condition is saying. Very straightforward, very simple. As I said, I think a lot of you have already seen this somewhere. Now, there are different approaches of finding this H function. We do not know how it looks like. All we know, like in the Yakov case, is if we can find such an H, then you have a safety certificate, and you can use this certificate, which is a control barrier function, to help you find a controller to make sure a system is always safe. That's all we know. There are various approaches for us to find this H. Like you can use a linear function, you can use a polynomial function, sum of squares to solve for it. Unfortunately, finding a barrier function or even the Yakov function is known to be a quite difficult problem. You don't really know what's the right template. You don't know what's the older polynomial you should choose, so you can always find one. At Penn, I think Nikolai also have some work on finding barrier function using neural networks. So we are using this idea where we want to see whether the expressiveness of neural network can buy us something. So that's the idea. So we're going to formulate this H function as a neural network. More than that, we want to also represent the policy as a neural network, as all the learning-based control approach do. Now we have two neural networks. H is a barrier function, U is a control policy. Both are neural networks. And a lot of people ask, can you just do one neural network? Of course you can. The structure architecture is something you feel comfortable with. You choose the one you like. You can have one neural network to represent both, but make sure you have the separate output for for H and for U. So we have two neural networks or one to represent these two things. Now, how to find the weight and biases of these neural networks? What we are going to do is a very straightforward way. And actually, the initial work was from UCSD, a group at UCSD. They show that if we use the following loss term, the single loss term, that for both, we will be able to find, theoretically, if it converges, we'll be able to find a barrier function and a control policy to make sure that barrier function is true for the closed loop system. Now, that loss function is actually a very simple encoding of the three conditions for the barrier function that I've just described. So I have color encoded both of them. The green one says when the states are unsafe, we want the barrier function's value to be non-positive. So we just penalize the case when it's positive. You sample states, you have some sort of a classifier that tells you whether the state or safe or unsafe. If it's safe, if it has a positive H, you penalize it. If it not, you just, you're happy with it. So that's the first condition. You can see the rest of the two are more or less encoded in a similar way. It's a very straightforward way of encoding this constraint. And so if I use a diagram to describe what I just said, we have neural networks as the representation and use the loss term to find it. Question.
How does V enter into this?
The V? Did I have a typo of writing V?
V should be H.
H? You mean the?
Yeah, you're trying to find H and U.
We're trying to H and U.
The infimum is over V and U. I think it's just in my foundation.
Oh yeah, sorry. That's a typo. That should be H. Sorry about that.
So what happens if U is a pre-trained neural network? Because I want you to satisfy many constraints other than just being safe.
Yeah, so we thought about this idea, like you can do this iteratively. You can find a control policy, then try to find a barrier function. If it doesn't work, it may indicate something for us to improve on U. I have to say that we were not very successful in terms of doing that. So basically, if you do not have U, you do not even really need that the third condition. But if you don't have that third condition, in a lot of the cases, if we don't do this, finding these two things at the same time and just use a naive vanilla machine learning approaches, then we will get a very flat barrier function. So like it seems to be a trivial solution to this problem. Like the barrier function seems very flat, like almost like a constant in a space that we have sampled. That's one issue we have found. That's part of the reason we're trying to find both like at the same time. Okay, so that is what I was saying. I'm sorry about that typo, should be a H over there. If V is a Lyapunov function, you can pretty much tell it's the same encoding, same loss term. Just change the H to V. That's the way we find the Lyapunov function. And if I want to show you how it looks like, what's the thing that we actually learned, I want to use two examples here. So what's in the middle here is like a navigation problem where you have this very simple obstacles that the pink region there, but the safe region now becomes non-convex. We want the vehicle, it's actually a drone that can start from anywhere and always reach the right bottom. You can see that first of all, the barrier we have learned is a blue curve, aligned pretty well with the outline of the obstacles. Of course, it's not perfect because the neural network we have chosen is relatively small. It's like a 2 hidden layer with like 64-ish neurons. It's not the most expressive one that you can use. You can definitely make it a larger one and it can align with it better. But you can see that even in this case, we kind of learn pretty well structure following that. And another part is saying the trajectory will always go to the darker and darker region. So ultimately you will reach that black region, which is the destination we want to go. On the right-hand side is a satellite problem. So basically you have a target satellite in the middle and you want another satellite to orbit around it. Now you don't want these two satellites to be too close or to be too far away from each other. So we have those two purple circles. So purple circle define the region. You cannot be within the small purple circle. It cannot be outside the bigger purple circle. But now if we look at the barrier we have learned, which is the blue curve, they capture that to the ring area pretty well. And we ultimately want the orbiting satellite to be stabilized around the ring region around the two green circles, so that the tiny ring, that's the darkest area. So that satellite will be stabilized around the darker region. So that's how it looks like. So far, so first of all, I want to say that it's not like these two problems are difficult problems that can only be solved. It's just like a visualization if you do this, then this is how it looks like. It's not like traditionally hard problem. You have to use neural network to solve for it. But the next level problem will be challenging for the traditional approaches when it comes to multi-agent system. So what I'm plotting here is a toy example. We have 4 agents. They're tracking their own paths. Now, I haven't put a collision avoidance controller here. So if they can't collide, when they collide, the color will change. You can see that's when they get too close to each other. My question is, how do we want to design a collision avoidance here? Of course, we can use a barrier function. It works. We can have a barrier function for if each of these agents have n-dimensional state space, you just take a barrier function of 4 n-dimensional space. And if you do that, actually can do a pretty good collision avoidance control for this example. But is a big centralized barrier function a good idea? I don't think so. I don't like this idea because of multiple reasons. First of all, I have 4 agents, that's probably okay. But if we have like a large, like the vision we have, like thousands of drones in the city, I don't think it's a trivial idea to train a barrier function for thousands of these agents if I treat them as a whole. So you pretty much need a neural network that can take a lot of like hundreds of thousands of dimensional input and have this scalar value of barrier function. It seems very tricky. Another aspect is quite difficult to generalize. What if I add another agent here? Do I have to retrain everything? Do I have to find a barrier function for every number of agent? What if like I accidentally lose one? I don't want to retrain everything. So that may not be a good idea. So centralized one is not a good idea. Then we were thinking, can we decentralize, like make this problem a more distributed version of the problem? For all these types of certificate functions, the good news is we can. It's actually pretty, they are in control domain by itself. There are already results. They are telling us how to do a decentralized version of these certificate functions. For the barrier function work, we actually find that we can decentralize the barrier certificate by allowing each of the certificate to take the observation. So here, if I list the decentralized barrier certificate here, you can see the three conditions look almost the same as what I described at the beginning, except that now H has two inputs. One is a state X, the other is the observation O. Now you may wonder, what is observation? It could be multiple types of things. The easiest one would be you can have a camera here. Of course, camera, if you have a camera input that always like a huge observation, it might be difficult for it to find. Here we can do a LiDAR measurement. That's exactly what we have done. We allow each of these agents to carry some sort of a LiDAR. The LiDAR will spin around, send a rays, and whenever it has an obstacle, it will be reflected. So that's the model. You can also even further simplify the observation to be just where your neighbors are. That's like the easiest observation you could have. But in this framework, there's even no communication. I will talk about like what's the potential issue here, but as of now, there's no communication. Each agent just observe what's around that. Now, in that way, we can decentralize the certificate. So ideally, we just need to find one for each of the agent. And if they're the same agent, we just need to find one copy for all the agents that share the same dynamics. And you may wonder, if I decentralize it, do I lose any of the guarantees that I had, like safety guarantees? Fortunately, it's not difficult at all to construct a global barrier function from the decentralized ones. So if we're able to find all the small HI for each agent, in this case, take the maximum of it. That's a global certificate. You're not losing the safety guarantee that you used to claim. So, and you don't have to train for it. Question?
If you do something like this, does it become too conservative? That is, then you cannot find the control policy that would.
So it is conservative in the sense that here we have to assume if you want different agents to share the same certificates, they basically have to share the same pattern, and that's the conservative. Like they have to be kind of agreeing on yielding the same certificate function, and then the behavior kind of like a more cooperative. In terms of like handling the adversarial behavior, it can become an issue here. That's something I plan to talk about. But yes, so that kind of make assumption that all the agents will obey to this thing that you gave to them.
Just a quick question. How do you locally compute OI dot without knowing your neighbor's control actions?
I will get to that.
Okay.
Yeah, so the 2 slides from now.
Just one question. So assuming that the local barrier functions are valid and satisfy the inequality, is it straightforward to show that the compound H also satisfies the inequality?
Yeah, you can. We have this proof in the paper, but it's quite straightforward to show the state H will satisfy those inequality. Okay, so that's like step 1. We decentralize it. Now, this decentralization step will cause a couple problems. First problem, this OI now it becomes observation. Observation will change, right? If you send LiDAR array spins out, you may have a 0 to the maximum number of rays number being reflected. So this observation will change. If you want to understand the positions of your neighbors, you may have 0 neighbor. When you're in a very sparse space, you have multiple agents in a crowded space. So we have to handle all these issues. Now to say that, before I was asking, what about OI dots? There's like a derivative of the observation. How would you expect that? So I have to deal with these issues. And I will tell you how we kind of use a few actually tricks from machine learning and something else to address these issues brought by the observation OI. Now, first step, to handle the case that OI, this observation is time vary in terms of both quantity and and permutation, we use something called a point net. It's a very like popular thing back in like 3-4 years ago in computer vision. People use basically you encode the fixed length, you encode the varying input into a fixed length vector. So I think this technique now is getting more and more popular in control domain. Back like 3 years ago, when we started to work on this type of problem, it was not a very standard thing to use. But now, so point net, the idea is you just encode the input through like a fully connected multi-layer perceptron and use a max pooling layer to fix the length. That's very straightforward, very, very simple. Then you have a fixed length vector to represent the OI and send it to the network. These years, I have seen a lot more work following this idea. People have used transformers there to encode like a camera or different types of encoder. It's like definitely something if you want to work on observation-based or perception-based control, it's something worth trying.
Is there one vector per LiDAR observation, or are multiple LiDAR observations coded into one vector?
It's like for this one is purely local. So for each of this is one agent at different step, but it has this array stand that is each vector correspond to a certain like reflection of that LiDAR observation. Yeah, so it's like purely locally what's the observation look like. Okay, so that's problem question.
Yeah, so but what guarantee do we have? So like for something to be a barrier function, we need to satisfy a set of constraints.
Yeah.
And now this observation is passed through this neural network, then I don't know anything about it.
That's a good question. So the short answer is definitely like it's hard to argue with theory. You can sort of treat this encoder as some sort of a mapping. If that's the case, like if there is a good one-on-one mapping through this encoder, then that we can still preserve the property that we want to have. But if it's not, which like we don't really know whether it's an exact one-on-one mapping, then we do not really have that strict guarantees that we used to claim. So it's like this type of encoder, and the next step will definitely lose a little bit of the theoretical guarantee behind it. Okay, now the next step is how we deal with OI dot. Basically means how your observation will change. Of course, it's hard to know that without really knowing what your neighbor is doing. So if for LiDAR, one of my students have this very interesting, very smart idea of how to handle LiDAR-based observations derivative. Now, basically, the idea is for a 2D or 3D vehicle, the control input will do, actually the control input will change the position and also heading of your vehicle. If you set the coordinate to be centered around the vehicle, that means the workspace translation and rotation. So that's kind of the mapping there. It's not mine. Sorry. I thought it was mine. From this workspace translation and rotation, if we map back to the vehicle with some affine updates to the LiDAR observation. Now, basically, to be able to do the backpropagation, what we're doing is to search over the control input space to understand this input effect to the affine transformation to the LiDAR observation. That's how we are approximating the OI dot. And of course, this is like a trick for LiDAR-based thing. For a camera, you cannot do this. For camera, we have recent work trying to encode using a generative model, the NERF work in computer vision to give us that prediction. Of course, like I have to say, what all these like new things we bring in will kind of lose a little bit of a guarantee here and there. In this case, like although we know the affine update to the LiDAR observation, but the array you cannot predict which one will not go back anymore. So it's like an approximation instead of an accurate understanding of OI dot.
Just a quick follow-up question on that. So suppose in this setting, rather than it being a static workspace, it's two of these agents, right, that are kind of trying to predict each other's observations. I guess that's kind of the question that I was more asking, because in order to predict OI dot, then when you need to know what the other agent is doing as well, or does this
Yeah.
kind of putting everything back into relative coordinates fix to help things a little bit?
Yeah, so I think one way to do it is to kind of know what your neighbor agent is expecting to know. And in this case, we actually assume the neighbors will do the same thing to you. You can use that information to do that prediction a little bit. And in this case, the setting looks like it's a static obstacle. Like if you're far away and the obstacle is not moving like super fast, it kind of if you update frequently enough, that's empirically that may also work.
Makes a lot of sense, thanks.
Maybe a follow-up question. I was wondering, do you need to make any assumption on OI dot in the decentralized condition to guarantee that it's satisfied? Because it seems like if you don't put an upper bound on OI dot, you will not be able necessarily to guarantee.
Yeah, for sure. Like if there's a dramatic change, like in this type of approximation, you kind of naturally assume that there won't be dramatic change. Otherwise, like if you turn all the arrays kind of are not reflected anymore, your prediction is going to be
Because
wrong.
there's a coupling, right?
Yeah.
The CDF of the other agent kind of determines the OI dot of the
Yeah.
my agent.
Yeah, that's right. There's some hidden assumption that is there, like to bond the dramatic change of this in this case for like basically we are using numerical way to approximate that OI dot. That numerical error shouldn't be too large, otherwise it will not work. Okay, so that's kind of like the background. You can see it's not like a new theory type of things, rather how we bring in these interesting technologies in machine learning and combine with the knowledge in control theory here to really make it work. So I will show you a couple of demonstrations first, and then we'll talk about the potential issues here. So here, first of all, how we are training here is we put these agents in four agents in empty space, let them run and collect data and use those data to train for a barrier function controller. Both are decentralized. On the right hand side, the left one is the original example problem I showed. On the right hand side, it's the how it works, how that decentralized controller works. You can see that, first of all, they're all using the same controller. They have their nominal controller to make sure they track their path. On top of it, there is a barrier function certificate controller that will work on each of the agents. When they are far away with each other, that function won't be activated. So you have an observation kind of range. Within the range, you can see where your neighbors are. If they're outside that, you don't really care when they're far away. You can see that how they kind of know how to avoid each other by turning relatively to the similar direction. And we also try to see how well this generalizes. So we use 8 agents to train in the empty space, let them run. Of course, if you collide, that's how we collect unsafe data. And use 8 agents to train for just one barrier function, one controller. The same controller will be used on all the agents that I'm showing here. In this case, it's like a Dubin's Cars model. We can see that from 30-ish agents all the way to more than 1,000, they're using the same controller. And whatever their nominal controller is asking them to do, they kind of learn how to coordinate with each other to avoid collisions. And you have a proof on the line there. I will give you several plots to show how that decentralized barrier function that we actually learned look like. But something interesting to observe here. First of all, from this example, you kind of tell what it really learned. What it learned is like a virtual roundabout in the middle, like they kind of follow the same direction to get like them outside of this super crowded area. And if you look at that 1,000 case more carefully, you can pretty much observe a similar pattern. So that's something we didn't expect. We didn't really know what's actually learned behind the barrier function. This is just one observation. We have done 2D case, this is a 3D case, relatively easier scenario. But actually 3D is easier to solve than 2D when you have like 1 degree of freedom to move around these agents. But I will show you how it looks like in the simulation environments that I grew up in at the beginning. Now, in this plot, I want to show you what is exactly the thing that we have learned. What is the barrier certificate? How to understand the decentralized barrier certificate? So these are two scenarios. The first one is both are ground vehicles. Now, what on the right-hand side is the local barrier function mass value in a new agent's eye. So the agent is not here, the agent somewhere not plotted here. But imagine that agent is going to, for example, insert from here. That is what in its eye. Really what is learned here is some sort of a sign distance function. And you can see that these like small like white things is the barrier that this neural network has learned. Now in both cases, but more than a sign distance function, in both cases, what it's learned is these type of barrier certificate will tell you how your policy should do. Like in both cases, will do the opposite of this unsafe region. So this is a visualization of trying to explain what has been learned here. Before I show you more results, both visualization results and also quantitative results, I want to quickly say that I've been using barrier function all the time to illustrate this idea, but actually all the certificate functions I mentioned at the beginning of the of barrier function, contraction metric, the centralized version, decentralized version, the way we learn them is actually the same. It's the same architecture. We actually didn't even change the architecture of the neural networks. It's the same way of encoding the lost term. Basically, there are constraints of these certificate functions, and you penalize the case when they don't satisfy it. That's how we learn those. Now, this learned proof here, this learned proof, I have to say that it is learned. So it's learned on the discrete. You have to somehow prove it actually hold everywhere. I will touch that question a little bit in a few slides. But if we have verified that learned proof, then it can be used as a certificate function.
So this certificate function is the same or different than decentralized barrier?
Oh, like you mean, for example,
Yeah, you were talking about barrier functions before, and then you jumped to the certificates. Are they the same thing? Are they different things?
so the certificate could be Lyapunov function, could be barrier function, could be contraction metric, could be a combination of any subset of those. Yeah, or all of them. But like as long as you have this, you know how the constraint look like, you can encode the lost function, like encode the constraint in the lost term. That would be the same procedure. So the learned policy here, of course, it can run in close with the plant. And now, actually, we have more than a policy. We have some sort of a proof. Even if something changes, like there are environmental changes or like the dynamics suddenly change, you can use the learned certificate as some sort of a guidance to help you adapt to the new environment. So this is how overall how it works for different virus type of certificate. And like if I show you how it looks like here, for example, we compare with reinforcement learning, the popular ones. This work was done at the beginning of 2021. These are the available approaches back in 2021 that could work on thousands of drones. So in the first case, we like a pretty stress test. In a sense, all these thousands of drones kind of get crowded in a corner of the city. We want to see how well the barrier certificate would work. Now we only follow one of them, just follow one of them to see how well it behaves. You kind of see that our approach, that drone kind of nicely work around the very crowded neighbor without having a collision. We also try this on a boat because boats tend to have very big inertia. It's like for reinforcement learning, it's a slightly difficult problem when you're
ever.
I heard something here, but I didn't. Do you have a question? I'm sorry. All right. So when you're already colliding to another boat, it's already too late to turn. You have to really turn in advance. That's probably why some of the reinforcement learning feel that they potentially control the boat to collide with kind of a collecting trophy there. Now, those are visualization results. We have some sort of a quantitative result. So all these things are collected in those simulation environments. We have ground vehicles, we have flying robots, we have boats. We're also trying to study some sort of underwater vehicle here.
So I kind of lost you there on the proof technique for the verifier. So because the proving would need some kind of modeling of the environment unless it's egocentric and then the proof things individually for each of the certificates, HIs. So how do you get around this problem of specifying the system on the LiDAR scale?
So the proof, if you want to prove it, you have to show that in the entire space, the better that the certificate has hold. And that definitely assume first of all, you have an accurate model of the, sorry, I didn't mention this. We didn't do the proof. I kind of stopped there after training, and we claim that using certain technologies, you can do the proof like neural network reachability. For example, if you have the accurate model, you kind of compute the reachable value of the neural network if they all satisfy what you want for the proof. You prove it.
Right.
But proving it is a hard problem.
Right. So what we the initial setup of minimizing the supremum and the formulation you had in the beginning, those are producing candidate.
Yeah.
Candidate certificates.
Yeah, right. All right, so here are some quantitative results. Average over the environments there. In each of the environments, we have more than 1,000 agents, and it's like 1,024. You can tell from this number, it's like a computer science student who did it, who doesn't like 1,000, but like the next one he will do is like a 248. Anyway, and here we measure two things. One is the relative safety rate. Basically, we count the number of agents that was involved in the collision over the whole entire number of agents. The y-axis is something that's also interesting. We call passive completion, but basically means you don't want collision avoidance to kind of cause a lot of delay. Of course, by being very conservative, we only allow one agent to move at a time. It's quite easy to make it very safe, but we don't want to cause kind of significant delay. So this measures how much of a delay it will cause because you want to avoid collision to each other. So there's some original time you set to reach your destination. Now, because of the new technique, collision avoidance thing we introduced, we do not want the agent to miss their original time by more than, say, 15% or 20%. If they do, we say they didn't accomplish their task. Like in these cases, they were never like they kind of either collide or they kind of cannot really reach their goal. Some method is being too conservative, just wait until the other agent pass and then go. That will cause delay. You can see that here, our approach is kind of doing pretty well for both, and almost 100%. It's like 96 to 100. And I do admit that I keep saying we want certificate, we want strict guarantees, but it's hard. That's where like all these approximations and all the uncertainties that we didn't consider in the training that will cause a little bit loss in the performance. It's very high, but not always 100%. Okay, and you may also wonder, does that mean I have to use more samples? Fortunately, you don't, because of the certificate type of technique, you kind of like reinforcement learning, you will have this single reward that kind of guide you to find a good policy. In our neural certificate-based approach, you have this certificate function that kind of guide you to find the right policy. That is more information you're bringing in. You're bringing in control theoretical information into the learning process. That can help us use less samples to get what we want. So if we measure the sampling complexity, you can see that we only use, for that previous cases, we only use 10% of the training samples to be able to get a very high safety rate where, well, like others, for example, the reinforcement learning, they kind of get saturated around 50% when it goes from 1 million samples to 10 million samples. And this sample number is, although it's like 1 or 10 million, it's like collected along trajectories. You actually do not need that many trajectories, just the number of samples. Each trajectory can give you 1,000 or something. And there's something I kind of do not have time to cover today, but happy to discuss the details, is about model, like error tolerance. Basically, the idea is you do not need an accurate model to be able to learn a certificate. We can use a surrogate model, like you can collect data, use neural network to approximate a surrogate model for the training of the certificate function. And this kind of approach can have good model error tolerance. We can tolerate up to 20% of modeling error. So this model you use for finding a certificate can be different from the actual model that's running, but we can still have very high safety guarantees here. And that's some.
I have a question. So what did you tell us what those PPO safe and TRPO safe are? Do they like you learn something and then you decide the reward by running some simulations and checking whether it's safe or not?
Yeah, so sorry, I should have talked about, those are all first of all reinforcement learning approaches. Constraint, policy optimization, like these are popular reinforcement learning approaches. And the ones we use specifically is like the safe version of it. Someone use this approach plus some technique to make it satisfy the safety constraint. And they all have different kind of technologies. There is a reward, for example, not having collision going to their destination, but they do have various approaches to encode this constraint of safety. All these things, they use different kind of approach. Someone, for example, the one use shielding with kind of create a safety bubble around you and always wait for each other to pass by. That's possibly why they cannot reach their destination on time.
Sorry, in my understanding, your method is kind of similar to actor-critic method, where your critic is the barrier function or the unlock function. Your data efficiency is because the unlock function is easier to learn than like a value function, or because like you have in your unlock function or barrier function, you have your dynamics embedded in place.
So first of all, I agree it's kind of similar to the actor critic. We actually wanted to use it in that way in a more like reinforcement kind of setting, and we've been quite unsuccessful. I'll be happy to tell you why it's been unsuccessful. A lot of the cases is because the kind of the RL rewards direction conflict with the certificate kind of direction, and that's when we cannot really make progress, and we didn't have very promising results there in terms of building a more active critic kind of structure than this more naive approach. This one actually works a lot better. I'd be happy to know how to make it work. And the other argument you have is like something like there's no free lunch. You cannot just magically make it just more sampling efficient. So this is definitely because you're bringing like more knowledge here. And the YAML function, barrier function, the certificates are easier to learn than the policies for sure. That when you see the training loss, the loss corresponding to the certificate always converge much faster than the policy loss. You have a question?
I had a question about the relative model error. So how do you generate, you started with a perfect model. How did you degrade the performance of the error? Did you add
So here is just some measurement. We have some model that ground truth, but when we use it, we do not know that model. We only use that model to generate data and use that data to approximate a model, like as if we don't know the model. And to generate the curve, you could, of course, you have to have the ground truth. Like you don't have to have the exact ground truth, but you ask the model to produce the data, and you can numerically see how diverge, how much of divergence there.
Precisely train, not adding Gaussian noise to the.
No, it's like when you're doing the training, you actually do not know how that model is. The model is only a executable model that can give you data instead of ask you to kind of go into the model and see how it is designed. And there questions.
So it means this learning scheme is kind of like imitation, but that you use the executable model as the expert to generate data fitting to them, but that will get this capabilities. Right.
Imitation learning, you have a policy, but here the model will only give you data, actually know the policy. You can randomly generate some policy and give you a data approximate the model. Like imitation learning, you still have some expert who give you the policy and you can mimic that. But here we don't have an expert that give us the policy. You are actually search for the policy. But that's a good point. I will show you some of the work we have done trying to bring this together with imitation learning. Another thing I'm like really excited about this approach. Like previously, we were just looking at a lot of agents, but those agents, the models are kind of like academic models from physics that people have constructed. And recently we have got this model is an F-16 model from Air Force Research Lab. They created this model they claim to be a high fidelity F16 model in Simulink. And I don't know how many of you still use MATLAB Simulink. It's like a nightmare. I didn't like it when I was a student. It's a little nightmare, like you just infinite click to get to the end, and ultimately you see like a lookup table, like what I'm going to do with this lookup table to analyze it. And sometimes like a hidden, some sort of a mask over some function that you're not even have access to open. So that's kind of the model like that. Of course, they have done some improvement. They have tried to have like a Python C++ like version of it. Anyway, all I'm saying is a difficult model to deal with. Now, what they want to do is to study how to add some autonomous functions on this F16. Now, the type of autonomous functions you can imagine is like ground collision avoidance. Like if you have seen Top Gun, it's like all the things that Tom Cruise can do in Top Gun, like a pull out when it's too close to the mountain, or you have like, imagine you have a sequence of waypoints in the valley, you're trying to follow that waypoints to avoid climbing into like the obstacles. You have a question?
What was the red dot?
Red dot is a waypoint. Yeah, so this is a particular case of waypoint tracking there. Like the sequence of waypoint is supposed to reach the waypoint. Imagine there's like a virtual valley, and if you don't track the waypoint, you're flying on the mountain. So that's a single system, not like thousands of it. But self is already very complex in the sense, even the Air Force Research Lab before, like they spend they have a hard time trying to find a good controller for it. It's just like a very massive kind of massive and messed up model. You can see here, like it's doing waypoint tracking, but it's not like perfectly doing that. So the reason is because if you push it in their model, in their controller, the Air Force Research Lab folks have their version of the controller built in a Simulink. If you push that a little bit closer to the waypoint, it will crash, it will lose speed and crash. It's a very tricky one. And of course, this model has its own problem of like numerical issues if you go outside the lookup table's range, if you just throw a random number. Now, we actually just tried the same thing. Of course, this one has 16-dimensional state space and 4-dimensional input. We use like actually what I just described to find a controller, various controller like collision avoidance and also waypoint tracking. The one I'm showing here is waypoint tracking because you will see some funny behavior produced by other approaches. So our approach, you can see that it can actually nicely track the waypoints very accurately without losing speed. That's the point. If we look at like the other machine learning based approach, that's why I put it here. Like, that's definitely not the most desirable way to fly that aircraft. I just feel that really because this airplane model is very easy to lose speed by spinning really fast. That's a way of not losing speed. So that's how the reinforcement learning and the imitation learning approach kind of packed into the way.
Is there a safety constraint that you put on your model to avoid it from or keep it from spinning?
We haven't. We didn't put this, just a stability problem. Like next waypoint is the equivalent of one. That's it. And the and of course, in the Yapple function, kind of ask your angles to kind of stabilize. So that's a constraint you can kind of imagine being put there. And the other, these are all the kind of machine learning approaches we managed to make it work. There are definitely other approaches we didn't compare. Some other kind of let the aircraft fly, but it still has some difficulty finding tracking all the waypoints. We have a similar result for ground collision avoidance. And this approach, we only use 5% of the data. You can see that on the right-hand side is the sampling complexity. We converge so fast that you can see that the reward can jump. It's the right-hand side. We zoomed in, have a zoom in view to the left, but it jumped to the perfect reward very quickly. Versus others kind of struggle a little bit.
Did you see degradation after this training, like above one E5 sample for your model?
We actually stopped there. Like once we find the Yapple function, we found a perfect Yapple function, we will stop there. Like the last term, we just converged to 0 and stop there. I don't know what will happen. Keep doing that. So is that your question?
Yeah, because when I train RL models, sometimes they just jump around.
They do.
Even after.
For us, yeah, we didn't, basically just didn't continue. Okay. Another thing I know I'm running a little bit like behind. I started a few minutes behind, but anyway, let me know when I should stop. Just
5 minutes.
okay, I will try my best. That's a hard, maybe 5 to 10 minutes. I will try to stop there. And definitely a very good discussion with all of you. I'm happy to continue the discussion. Another thing we have tried to do is to understand whether certificate can play a role in not vehicle models, but like data-driven models. So the idea here is in imitation learning, in traffic kind of modeling, human behavior modeling, a very popular technique is imitation learning. Basically, we have a traffic data, and from the traffic data, we're trying to mimic how humans react to different traffic scenarios. And that is a very popular thing back like a few years ago. And what we are trying to do here is trying to understand whether certificate can play a role on the data-driven model. So it's no longer a vehicle model, but the model is learned from traffic data through imitation learning. And then we try to use the decentralized variable certificate to capture the collision avoidance intention of the human beings. Like you kind of get a pattern of the intention of the human being and parameterize it, some parameter in barrier function, insert that in the imitation learning process. And in this case, for example, all these things like the cars are driven by human. In this scenario where there's a biker trying to get across here, the setting is very similar to what I have described. There's like decentralized way where each human being have an observation of the neighbors. They will follow what the imitation learning model tell them, but on top of it, they have this barrier function to avoid being too close to others. And by doing that, we observe a couple of interesting things. First of all, we feel that it will make imitation learning a little bit more reasonable. So here I have the case of the pedestrians. Every one of them kind of have a data-driven model behind it, learn from data. They are getting across the intersection. Now there's a car running from right to left. This pedestrian in the traffic data, they never saw the car before. It's like a new thing to them. We want to see how they generalize. And the car is just a very simple MPC controller behind it to say you want to move ahead, but if you're getting too close to people, you should, move away from people. And we can see that in a fixed trajectory, of course, it's like these people will just ignore the traffic. But in imitation learning, when they see a new car they never saw before, they kind of go crazy. Like this behavioral model is not really explainable. You don't know why these folks kind of suddenly decide to move to left when they see a new car.
Is this trained on Philadelphia data?
No, it's just that's and for us, you can see like by adding the barrier function, they kind of when the car is moving slowly enough, if it's just adding the barriers into imitation, they kind of behave more realistic, and like the barrier function is asking them to move away from the obstacles.
So how do you find the closest control input that satisfies the barrier function if the imitation learning approach gives you something outside of the safe space?
Yeah, that's a good question. So in this case, they're actually used sort of separately. The imitation learning will give you some sort of nominal behavior, and you always want to be close to that nominal behavior while satisfying the barrier function.
So you just find the closest.
Yeah.
And that's it.
Yeah. Now, like on different data sets, you can see like that's Stanford data set, that's Stanford intersection. You see like the bikers using pure imitation learning, the bikers kind of over pedestrians. It's just not the most realistic scenario, but for us, we kind of have a more realistic behavior on this model. That's like I like to study more of this like use of new certificate in different settings. This is just an initial trial, and this is like the simulation in the simulation environment. You probably have already seen most of them, but if we put the drones in a more reasonable and more sparse way, this is following one of them, but they're all running the same controller. You can see this is how they behave. And there are a couple of other uses I will just very quickly go over. We have used the same approach that is called the other same applications using certificate functions to do very precise drone control against the propeller wash. Propeller wash is like the wind effect reflected by background or the obstacles or the work close to you. That's very complex turbulence. There are like researchers who study how to model those turbulence as neural networks, but that will make the model very complicated. Now, using the neural certificate approach, you actually don't really care what that model is, but the same kind of structure of doing that. We also have done like vehicle tracking with like a slippery road, where we compare that using neural certificate, you can actually run the controller at a high frequency, but using robust MPC, because at each step you really have to compute the online optimization problem. If your frequency is too high, it's less than real time. You cannot finish the computation, but it's too low, you kind of slip away from the original track. There are also hardware demonstrations, like everything I'm going to show here is just like you train in the simulation environment using some sort of surrogate model directly put in on the hardware. In this case, like two robots trying to push a box to the desired location. There you can see like you can arbitrarily poke that box away, but it's doing a quite robust job of that. We have tried arms, where in this task you are giving an arm a load that exceeds its maximum load, but you do not want to see a dramatic change there on the arm. It will harm the motor of the arm. By adding a barrier controller, you kind of see that can smoothly react to that large load. We, in terms of just navigation, here you can maliciously block the vehicle there by throwing an obstacle in front of it. There are tricky cases where you use naive slam and planning. It can kind of that robot kind of gets stuck, but on the right hand side, because of the Lyapunov function and barrier function that you have on top of it, kind of smoothly avoid that obstacle. It actually worked pretty well, unless you just throw the box on top of it to be able to navigate away from it. Okay, so I want to finish very quickly by, I know there are always some questions being asked for this line of work. I want to address the questions just in case you have those. First questions, there are always this question of, is your learn certificate function really a certificate function? The short answer is no. In training, you use finite number samples. There's just no way for us to just directly claim this is a valid certificate function. There are other ways to verify it, as I was trying to explain to Surrogate. We can do a robust version of it. When you sample very densely, and you make sure the samples are close to each other. You make sure the Lipschitz of your learned thing is not too big. Then because of all of that, you can have a global guarantee. Or you just put everything through a neural network verification tool to give us a result. But I have to say, there's no free lunch. If we want to make a deterministic guarantee of the certificate, it's going to fix the curse of dimensionality. I totally agree with that, and I don't have a good strategy to get around of it. But ultimately, to make very strong guarantees, that's kind of the cost you have to pay. That's just my personal opinion. And second question people always ask is your comparison with RL is not fair because you know more information. And I would say, yes, we know more information. That's why you can get the good performance and the good sampling complex. It is not like you didn't introduce any domain expertise knowledge and you get all of these things for free. Definitely because we introduced the domain knowledge, we kind of improve both sides and kind of jump out of that trade-off line. But that's my personal takes. I'd like to study from all of you how to have a better version of these claims without really facing the curse of dimensionality. Question? So the CBF-based RL, to my knowledge, I only know the one from Stanford. And that's why it just doesn't work. I actually talked to the professor who is a good friend. He said it's just not very useful. I mean, the one, there are CBF RL where you know the CBF. Those things we don't because we do not know the CBF. There are CBF RL that we do not know the CBF. That's the only one I know is from Stanford, and it couldn't really scale up to the large scale cases. Okay, so I know I promised to stop here. Just very briefly mention because I only talk about control, but actually in planning, there are a lot of interesting problems. What we are looking at is how to do planning from temporal logic-based specification. I trust that a lot of you are familiar with temporal logic. It's basically a formal, mathematically rigorous specification that kind of encode all the temporal, logical, and spatial guarantees. Now, there are a couple of examples I will skip here, and there's a toy example trying to explain what is temporal logic, but basically in this case, there's a robot trying to go to the destination, but it cannot go there directly because the doors are closed. You have to pick up a key at the corresponding area. It's like playing a game in your phone. There are some logical constraints here. Before you can open the door and get through, you have to pick up a key. So these things can be easily encoded in temporal logic. You can also have your timing constraint. So for this line of work, we are looking at motion planning from temporal logic. It's following similar line of work, trying to bring together machine learning, but this time with a certificate that's given by temporal logic. We have done two lines of work. One is to do motion planning from it's a non-linear based approach, but for this type of problem, where you can see how it's solving this. But from the temporal logic, we can automatically generate a plan that can satisfy the temporal logic. And recently, what we are doing is to bring in graph neural network, trying to graph neural network based neural structure, trying to improve the encoding of temporal logic and make it more efficiently. I will stop here with this video. So that's basically how that will do. In this case, it's like a planning work with multiple arms trying to assemble different things together. Now, there are collision avoidance constraints, but the pieces actually have dependencies. You see, when the two arms trying to hold, like it's holding this piece before the other guy is putting it up. On the top here, you can see that arm is holding a piece because the bottom one is there. It's not there. It has to wait until the bottom piece is over there before you can drop the piece. So there are dependencies and underlying all the different pieces. The planning work will try to follow this temporal logic constraint and generate a plan much faster. So we managed to achieve like 95% of time reduction in terms of online planning. But I'm sorry, I didn't really go deep into this line of work, but that's kind of on top of control. If you have a pretty good, pretty robust low-level control at a higher level, this is like the also very interesting line of work we can do for planning. We're also planning for the drones. Basically, how it works together is you have some sort of temporal logic constraint. This type of planner will give you the destination for each of the drone. And now the drone will just fly there. When they get close to each other, you can use a lower level certified controller to avoid the collision with each other. So I will stop here, pause here, just for more questions. And thanks for being very patient with my like really overly run presentation.